And then last but not least, we'll let David start about his discussion on developing and evolving your own optical or IP control plane. Thank you.
Thank you. So my name is David Rosso. I'm a network systems engineer at Fastly, and now I'm going to be talking about developing and evolving your own control plane. So this talk is going to have three main parts. I'm going to jump back to 2013 and explain why and how we built our own control plane. Then I'm going to jump to 2015, and I'm going to detail a bit how we rethought our original control plane, and we started just trying to iterate on it. And then finally, we will go to early 2017, when we had already finished designing our new control plane, and we were started working on a migration plan to go from the old to the new control plane. So without further ado, let's start. Let's go back to 2013. So in 2013, the company was kind of in the early days. So we were setting requirements for the network infrastructure. So the first requirement was that we wanted to have multiple transits on each POP. That was mainly for performance and reliability reasons. Like, you don't want to be just tied to a single transit that has a bad day, and then all of a sudden your entire service is gone. The second requirement was that the company was fairly new, so it's impossible to predict usage or growth. So the architecture had to scale out horizontally with demand. And then finally, we have to connect those hosts to the network. And again, it's a fairly new company, so money is kind of a constraint. So we had to be able to connect all those hosts to all those transits in a cost-effective way. When you start thinking about connecting to the internet, especially if you are thinking in connecting to multiple transits, and each transit has like its own routing table, the first thing that comes to mind are routers. However, routers are expensive. So if you don't have the money, or you want to build a network that scales economically reasonable, that's kind of a problem. Also, routers have a lot of bells and whistles that you might not care about, and all those features might lead to bugs that, okay, why is this broken? I mean, I'm not even using these features. And also, routers back in 2013, they were kind of limited to the best path forwarding or to policy-based routing, and I will get more into details later. So yeah, routers didn't look like a really good option for us. On the other hand, you have switches. Switches, they're super cheap. The port density is great, which means that you don't need that much space to rack them. They don't consume that much power, which is good, because that means that you can have even more servers in the rack. However, it has some limitations. Like, for example, you cannot fit all those routes that you are going to be getting for your transits into the FIP. And also, back in 2013, switches only cared about IP and Ethernet, which means that if you want to start doing overlays or stuff like that, that's not an option. In 2013, the team were mostly comprised of 2 network engineers that were dealing with everything in the network, like from operations, provisioning, procurement. They were basically too busy to care about dealing with vendors and asking features and making sure that the vendor would implement them correctly. And we also had 2 software engineers, although one of them was the CEO, so arguably didn't count because he had better things to do. And they both had an open source background and hated network vendors as a whole. And last but not least, they were determined to push the control of the network to the application. Like, usually you control the network from the network itself, like by setting policies or whatever. But we wanted instead to push that responsibility down to the application. So at this point, the team came to the realization that routers are expensive, and they don't do what we want anyway, because we want to push the responsibility to the application. They are super expensive, and their port density is not good. So not only CapEx is going to be bad, but OpEx is going to be bad as well because of power consumption, rack space, everything. On the other hand, switches are cheap. but they have certain limitations. However, in 2013, there was at least one vendor, maybe two, that were running Linux and would even give you access to program the switches yourself. So we decided to build our own control plane. How hard can it be, right? I'm going to be hand-waving some of the details now of that original control plane. You can visit that URL if you want to go more into details, but yeah, I'm going to summarize it a bit now. So we're going to be using this network just to illustrate how the original control plane works. It's just a host, a switch, and two transits. So the first thing is that we have a layer 3 segment on each link going to the transits and another layer 3 segment going from the switch to the host. If we check the layer 2 and layer 3 tables on the devices, there are no surprises, right? We have the FIP with the connected networks. We have the ARP table with the neighbors on those networks. Nothing really surprising. Now we run IBGP down to the host, which means that when a prefix comes in, we get those prefixes installed in the FIP of the host. However, remember that we are dealing with switches. We don't have space to put the full routing tables of all those transits into the FIP of the switches, so we don't install anything on the switches. We just send them down to the host. But what happens now? It turns out that the host now wants to send traffic to 172.20.01, right? So it just does, the host will do just a route lookup. It will see that it can send the traffic via those two IPs, but turns out that it doesn't know how to reach those IPs. You would traditionally solve this problem by running an IGP and having a recursive route lookup. However, remember that the switch doesn't know how to reach 172.20.00/24. So if you would use an IGP, you would be black holing traffic on the switch instead. So here's the trick. We put everything on the same layer 2 domain: transits, switches, and host. I know it's gross, but it works. Now, you synchronize the ARP table from the switch to the host. You send all the ARP entries that belong to transit. So now, if the host wants to send traffic via the blue transit, the only thing it has to do is set the destination MAC address that corresponds to the router of that transit. And the switch will just do what it knows how to do best, which is switch traffic. And if the host wants to send traffic via the orange transit, just a matter of setting the corresponding MAC address. And now we can build tools like this one. This is an internal ping tool that we have, where we can actually ping a destination over all the available circuits on a given site. So you can see here we have like a bunch of circuits, and we're pinging the same IP, so we can see the latency and packet losses for that particular IP over all the transits. So that was the original control plane. So now let's see how we worked on it over the years as we gained experience and the team grew. So time passes and things are working fine, but it turns out that the old control plane had a few architectural shortcomings. I mean, unsurprisingly, layer 2 hacks don't scale well. And sharing layer 2 with transits has some minor issues. You have to start filtering broadcast traffic, which is not a big deal, but you have to remember to do. But more importantly, not having a clear separation between layer 2 and layer 3 is just confusing for people. Like this synchronizing ARP entries and not having doing a recursive lookup, checking the ARP table instead of a connected route, that's just confusing for people. So we wanted to address those issues. Also, the previous control plane didn't support IXPs. IXPs, per definition, they're already layer 2 domains, and you're not going to connect your own layer 2 domain with someone else's, because that's just calling for disaster. So what we were doing with IXPs was to install routes coming from peers in there into the FIP, which means that we were running into FIP limitations in big IXPs like AM6, DKX links, etc. The state of networking in 2015 was pretty much the same as in 2013, but there were a few differences that changed completely the game. It was the early days of segment routing on BGP-LU, which basically went very well with what we were doing. And switches started to have like more modern ASIC that could do encapsulation protocols like MPLS or VXLAN. So that kind of was interesting for us. Now the team had grown quite a bit. We had now 6 network engineers, still busy doing all sorts of stuff. But we have 6 software engineers to work on an actual solution that involved less hacking and more doing things properly. So now I'm going to be describing the new architecture. I'm going to be using this leaf edge network, 1 host, 2 transits. So now we have only point-to-point links. No more layer 2 shared between transits or multiple devices, only point-to-point links. Now we run eBGP down to the host instead of IBGP. We assign an MPLS label for each egress peer. Any circuit that takes you out of the network has a dedicated MPLS label. And we start MPLS on the host. So we're not only running BGP on the host, we are also running MPLS on the host. So now, if the host wants to send traffic via the blue transit, it only has to select the MPLS label corresponding to that transit. And if it wants to send it via the other transit, just put the other label. OK, so that was more or less an overview, but let's see a bit more in detail how it works. We first assign a label at provisioning time. So you provision a circuit that assigns the MPLS label. Now, Silverton, which was the control plane tool that before would propagate the ARP entries, now propagates the LSPs down the network. So every time that you provision any circuit, the label gets assigned on the edge, and Silverton just announces that down the network. But here is the interesting bit. When a prefix reaches the edge of the network via a particular transit, we tag with an extended community that prefix with a community that identifies uniquely that LSP. So you can see, for example, those prefixes coming from 2 different networks. Each one is going to get assigned that extended community that identifies the particular LSP. And now on the host, we only have to extract the extended community and read which MPLS label to use in order to use that particular path. So now the network is super simple. It's just a bunch of MPLS routes, nothing else. You have MPLS label 1020. Just pop the label and send it this particular path. We don't have any more this layer 2 to layer 3 translation stuff doing weird things. This is just a route, so I can show you how the community maps to labels. So we have a route coming from 2 different switches. We can see on the first switch how the extended community 8086.1020 maps to the MPLS label 1020. And on the other hand, the other switch has the extended community 8086.1024 that maps to the MPLS label 1024. So, OK, now we have this network that is able to send traffic via multiple transits on a flow basis. So we need to expose that information somehow on the host so the application can make use of it. So the way we do that is we create a routing table for each particular egress peer. So here we have 2 different tables. And those tables, the only thing they have is a default route saying, if you want to exit this way, use this MPLS label. And then we just have a bunch of IP rules. This is a Linux construct that says if the socket has the forwarding mark AE, do a lookup on this particular table. If the forwarding mark is 513, do a lookup on this other one. So if we want to send traffic via, I think this is Cogent. So if you want to send traffic via Cogent, for example, the application would just open a socket, put the option, the forwarding mark option as AE, and that would cause the kernel to do a route lookup on that particular table that says, okay, you have to use this MPLS. And if the application doesn't know how to do this or doesn't care about this, you can always default to the main table of the Linux host that will just have all the routes in there, and then it's just a matter of writing BGP policies as usual. So in retrospective, we managed to rebuild the control plane using, well, maintaining the nice features that we had in the previous one, which means per flow routing, while addressing all the shortcomings of the previous one. And so far, everything has been working as expected. OK, so now we have two control planes. We have the old one and the new one. So it's early 2017, and we want to work on a migration plan so we can migrate the old version of the control plane to the new one. So we had a set of objectives for this migration plan. The first one is that we had to migrate from IBGP to eBGP, because IBGP is what the old control plane was using, while eBGP was being used in the new one. And the main objective with this migration was to make sure that we weren't running multiple control planes, because that means that you have to maintain twice the code. You have to maintain twice the tooling as well. And you have to train people to be able to operate multiple different networks. And then finally, I mean, if you have twice the things running in your network, it's just twice the things that can fail. And then finally, we wanted to make sure that this migration wouldn't take like years. So you have to migrate like 40, 50 POPs, I mean, just between finding resources to do it, notifying customer, scheduling maintenance windows. I mean, that can take just forever. So we wanted to make sure that this wasn't going to be an issue. But why is it an issue? It turns out that migrating from IBGP to eBGP has a couple of problems. The first one is that if you're going to start changing ASs in your network, you have to synchronize them. If you don't make the changes at the same time in all the involved devices, you're just going to bring down your network, because yeah, you have to have the local and the remote ASs in sync in both sides, or yeah, authorization won't come up. And also, IBGP and eBGP prefixes are not compatible when it comes to ECMP routing. So you have like these three routes that you can use. As soon as you migrate one of the devices to eBGP, that device is going to start attracting all the traffic, because eBGP wins over IBGP, and that might cause some congestion issues upstream, which is bad. It's just going to disrupt the service. So how do you solve these problems? Well, if you ask a traditional network architect, you're going to basically get nope. You can basically do it. However, we have software engineers, and we just take RFCs with a pinch of salt. So we just hacked our way into this migration. So the first problem is the ASN migration, right? So this is actually easy to solve. We just came up with a secondary AS keyword that basically says like, okay, if my neighbor is coming with either this or this AS, just accept it, simple as that. So now I can just flip the local AS on one of the sides, and the migration is done. Like, I don't need to synchronize multiple devices at the same time. I can just do one change at a time. The second problem is a bit trickier. Is how do you make an IBGP prefix compatible with an eBGP one, so you can actually have both prefixes, both routes in the same ECMP route? So the first problem is that eBGP always wins over IBGP. So we developed this knob that says compare as IBGP, which basically says if a BGP session has this knob enabled, treat incoming prefixes as if they were IBGP when comparing against another IBGP or eBGP prefix. So this is not a problem any longer for us. However, you're just moving the problem somewhere else, because now it turns out that the AS path on the eBGP side is going to be longer, because eBGP keeps prepending at each hop the AS of the router, announcing it. So we developed this other knob that says skip private AS path prefix, which basically what it does is when computing the length of the AS path, ignore all the leading private ASs. So now, because the leading AS in the AS path is 65,000, that's just going to be ignored. So the length of both prefixes are just going to be the same. And then finally, we were using local pref to signal various things in the network, and eBGP doesn't transport local preference. So we just added another knob to be able to transport local pref between eBGP speakers. So now that we have all these knobs, the migration process is as simple as follows. During the step 1, you just enable the secondary AS that you want to accept, and all the other knobs. Compare as IBGP, skip, private AS path prefix, allow, BGP, local pref. And this change is completely innocuous. It has no impact whatsoever. So you can just deploy it everywhere without any maintenance whatsoever. And then step 2 is just as simple as flipping the local AS on each device. And because we made eBGP and IBGP prefixes compatible, this change is going to cause a BGP session to flap, but it's not going to cause any traffic to flow differently. When the session is up, all traffic will flow as it was flowing before doing this change. So thanks to this, we don't need to start scheduling maintenances, draining traffic, notifying customer, because the change is not going to have any impact on the network. Here is an example. We have this prefix that is coming from 2 different switches. One of them is an iBGP speaker. The other one is an eBGP speaker. You can see that the AS path is completely different. The eBGP one is way longer. And you can see that the local pref is being transported as well on the eBGP speaker. So finally, thanks to all the knobs, we have this ECMP route that is taking into account both next hops, not only one. So yeah, so now I have a few closing remarks. Pretty sure that now you're thinking if we consider this or that. So I have a few preemptive slides. The first one, did you consider OpenFlow? Well, I'm just going to let the GIF play a few times. Yeah, I'm not going to make any comment. Did you consider segment routing? So we did. Segment routing, the core ideas are great. I actually like segment routing a lot. Main problem for us is that segment routing was super complex for what we wanted to do. I mean, we just wanted to do egress peer selection. So like 99% of the features of segment routing they didn't really apply to us. It also solves half the problem. Like segment routing kind of still keeps the control of the path in the network, either via a BGP controller or via policies. And we wanted to push the control to the application. So it didn't really map that well with what we wanted to do. And also, there was no open source option. And for us, I mean, we have a few developers, but we don't have all the resources to develop everything that segment routing entails. I don't even think that any vendor actually supports segment routing yet, at least not in a GA manner. BGPLU. So this is interesting. This maps a bit better to what we are doing. However, it has the same problem as segment routing as it keeps the decision of how to route traffic on the network. And again, we wanted to push it down to to the application. Although I think it's the right thing to do, and we might in the future revisit the solution and maybe implement BGPLU, at least to transport the information about MPLS, which we do today with the communities, but that has a few complexities. There is no open source implementation for BGPLU, and the trick with BGPLU is that you require a new address family, and you have to synchronize both address family, because BGPLU requires you to do a recursive lookup to know how to reach the next hop of the route that you got via the regular IPv4, IPv6 address family. So yeah, you have to start dealing with race conditions. So it's a bit more complex to implement. And yeah, to summarize everything, we built what we built in 2013 because there was nothing better. Routers were super expensive. Switches had certain limitations, so we had to work with them, and that meant doing all these horrible layer 2 hacks. Having the custom control plane was critical because we saved a lot of money and time, and it also allowed us to attract talent. When you have this cool solution, it's easier to hire people than when you're just doing things as usual. And then finally, we just revisited the solution when the team was larger and there was less hardware constraints, so we could build something better. We finally hacked our way into this seamless migration, which makes a lot of a difference. And open source was critical, because without open source, we couldn't have pulled this off, because resources would have been an issue. And this is everything. If someone has questions, I'll be happy to answer them. So, yep.
Ryan, Datalink, Inquisitor, and Witchburner. You mentioned it last slide, you saved a bunch of time and money. Can you quantify that? I mean, that's 4 years of development, and it's software development salaries. You know, how much did you actually save by doing this?
So with time, I mean time in getting things done. Like if you need a new feature and you have a traditional vendor, how long does it going to take? It's going to take years. You have to you have to talk with your SE. You have to make sure that they get it in the pipeline. Then they have to develop it. Then you have to upgrade all your network so you have that new feature. So saving time, I mean, we control our own software, so we can just develop it and deploy it, and we have the feature already. And money, well, I mean, if you have like, I don't know, like 2,000 network devices, and each one costs like $20,000 compared to $500,000, it's an easy math.
Matt Petak, Yahoo. This sounds really great. Now, I couldn't help noticing that you took some of our learnings from the past 20 years about BGP and sort of said, well, you know, worrying about loops and things like that really isn't necessary in this case, so we're going to ignore things like AS path length, and we're going to change around the route priorities. In your simplistic diagram here of just kind of the why of A, B, and host, it looks fairly straightforward. Did you have any situations where the tweaks you were doing caused any potential loop situations or unexpected, why are my packets going that away instead of this away?
Yeah, so we're ignoring the AESs, the leading AESs, for the sake of computing the length. So we're still doing the regular prevention loop.
Oh, so you didn't just completely throw them away. They're still being considered. You just truncate the length.
Yeah, it's just when computing the length. So like just ignore them now that you're counting them. But then when you're checking them to make sure that you don't have a loop, you still use them.
Okay, thank you.
Me? Oh, sorry. I guess I have it. Dan Mahoney, ISC, over here.
Sorry.
Sorry. It looks like you're using a lot of mainline Bird. Have any of those changes made it back into the mainline?
So we have upstreamed everything, both in the kernel, because we had to do a few kernel changes for the for supporting MPLS on the host, but everything has been submitted to the respective upstreams. Bird hasn't approved yet all the patches, but they are there. So you can either press them to accept them or just download them and apply them yourself.
Excellent, thank you.
Hi, David. I'm Ernesto. By the way, awesome projects all the way back to the Spotify SIR project.
Thank you.
My question is, in regards to one of the things that you address here is kind of peering engineering on the egress. So do you support for the same destination prefix sending traffic to more than one interface? And if not, then how do you address the situations where a certain prefix attracts a lot of traffic on one interface? So when you switch from one to the other, that's a lot of traffic shift.
So this is for egress, right? Like if traffic is being sent from the transit provider to us, there is nothing we can do there with this solution. It's just a matter of AS path, prepending, met changing, blah, blah. And regarding supporting sending traffic to the same IP via different transits, that's the whole point of this. So you can send traffic, like that was the ST ping example that I showed, where you're pinging to the same IP via all the circuits at the same time. So you can get metrics in real time over all of them.
Okay. And there is a feedback loop in terms of utilization as well, or I missed that part?
Well, I mean, the bandwidth utilization, you mean?
Yeah. Is that part of the considerations?
Well, that's kind of a different topic. Like that tool is just a wrapper around ping to be able to ping around through all the circuits. But you could start measuring things and taking that into account, so the application could decide which one to use. But that's kind of like more like a congestion control mechanism, I guess. So it's kind of out of scope of this particular tool.
Okay. Thank you.
So Linux and MPLS stacks are, that sounds weird, don't exactly the most high performance stack there is. Did you guys figure workarounds or?
Performance-wise, it's no problem whatsoever.
You have no issue?
I mean, we have been measuring things, and we get exactly the same throughput with IP, or like regular IP and MPLS. Like for us, it was, I mean, that's the reason why we actually used MPLS. We were evaluating VXLAN instead of MPLS. But the thing is that the NICs that we had didn't support hardware offloading for VXLAN, but they did for MPLS, which meant that we could do MPLS without losing any performance whatsoever, because it's done in the NIC.
Oh, so your NICs support MPLS offload?
Yeah, you can actually see, like there were at the very beginning a few performance issues, but those were just bugs in the kernel. So you can see the first two links that are actually going to kernel.org.
Yep.
Those are the bug fixes actually making sure that performance-wise they behave exactly as regular IP.
Oh, cool, nice, thanks.
Joel Yegley, Fastly. Just one comment on that. I think one of our experiences with this was actually that the stuff is substantially better than it was 2 years ago, which is, I think, a big improvement with respect to MPLS performance. So the inclusion of the stuff in the kernel has actually improved since the early era of it, and it's now tolerable. Also, TOE helps when it works, and it doesn't always, but it's still acceptable without it, still, at this point.
Gaurav Davra, Cisco Systems. I'm just curious how many labels you have to support on the host?
So today we are doing only one, because we use it only for egress path selection. We assign globally unique labels to each circuit. So today we only need to do one. We're going to start soon testing with two, just to see how it works. But today we're just doing one. Okay. Well, thank you.